Okay. So the first thing is we have to define a few things. So this is what's called a relation. Anybody know what a relation is? Yes, it can be a function, doesn't necessarily have to be. A relation is any set of ordered pairs. When we talk about ordered pairs, we generally talk about x, y. X comma y is a coordinate point. So if I gave you a piece of graph paper, and you throw darts at this piece of graph paper, wherever the darts land on this, you would list them all out, and that would be considered a relation. If it landed in a perfect circle, that would still be a relation. So that's a perfectly fine relation. So it's a random set of points or an organized set of points. It really doesn't matter. It's just any set of points that you want. A function, on the other hand, is a relation. So it is a set of ordered points, but it's not in a random fashion. So there's a little bit more specifics going on, where every x value, known as domain, has only one y value associated. With it, other than the x value. So a function is a relation where every x value, the domain values, has one associated y value, and the y value is called the range. So basically it boils down, for every domain value, there's exactly one range value. For every domain, there's exactly one range. We're going to say what a function is in many different ways today. This is one of the definitions that make it specific, but very few people can actually work with that definition. It's kind of long-winded. So we're going to have to come up with better ways of saying what it is. All right. So let me give you two sets. Set A, set B. Ooh, set B. Set A, -3, 1. -2, 5, 4, 7, -2, 0, and 3, 1. That is definitely a relation because it is a set of ordered pairs. All right, let's let set B be -3, 0, -2, 5, 4, 1, 2, 5, and 3, -1 is also a relation. So both of these sets are relations, but only one of them is a function. Which one's a function? B? Why?
Because A, the 1 repeats in Y.
The 1 repeats in the Y? So you're saying this can't happen in a function. Hey, Tom.
How you doing? Is there a Megan Black in this classroom?
Is there supposed to be?
Is this the late starting pre-cal class? Yes.
I think she's supposed to be, but she's not here. Yeah. Okay.
She's not in here. Sorry.
So does that fit the definition that a y value repeats for different x values? Now it's -3 and 1 and +3 and 1. Does that say every domain has only one range?
I was saying that B is the function, and that's because A has...
Those 2 1s? No, that's not why. A has 2 -2s. This -2 is associated with 5. This -2 is associated with 0. Having repeating y values is irrelevant because if I remember, I put this one as repeating 5 and 5. But this -2 is going to +5, and this is a +2 going to +5. That's perfectly fine. in my mind, the way I think of functions is that it's pretty much asking somebody their height. How tall are you? How tall are you? And different people are going to have how many answers? I'm 5 foot and 6 foot. That doesn't make any sense. They can only be 6 foot, 5 foot, 4 foot, 4 foot and a half, whatever. But you can have two different people exactly the same height. That's what this situation is. You have person -2 and he's 5 foot tall, and person +2 and he's also 5 foot tall. That's perfectly fine. Here, though, you can't be 5 feet and 0 feet at the same time. That just doesn't make any sense. So the top one is just a relation. You at least pick the function out, right? And the bottom one is a function. By the way, if I ask a true-false question on a test, I don't expect just true and false. Generally, I ask false ones, and then I ask you to explain why. So if you don't understand why they're false, then you really don't know why. So that's a good setup, but that leads into another definition of what a function is. What forced this one not to be a function, just by looking at it?
The x repeat.
The x's repeat. So a function can also be thought of x values never repeat with different y values. And the reason I put that second part in there is just in case you have a set that looks like this. Is that a function? -2, 1, -2, 1. Yes. Why? It's just talking about the point itself twice. That's perfectly fine. And this domain, he's -2 and he's 1 foot tall, and he's -2 and he's also 1 foot tall, but you're talking about the same person. Not that you're ever going to see something like that, it's just, it's a possibility. So that with different y values kind of gets rid of that, that this is not a function, this is definitely a function. Okay, next up. Equations, and how to determine if they are functions. The big thing here is the question mark. So I'm going to be looking at an equation and trying to determine whether it's a function or not. Okay. So if I give you x squared plus 3y is equal to 8, does this equation represent a function? In other words, if I throw in a bunch of x values, does it generate exactly one y value all the time?
No.
No? How would you find out?
Because the x is squared.
I don't care.
You could plug in a number.
You can plug in a bunch of numbers, but there's how many real numbers out there?
A lot.
What do you mean a lot? A lot. What is a lot of numbers? Infinite. So it's impossible to test an infinite number of x values in here to see if it generates exactly one y value. So the hidden direction for most of these, solve for y. Get y by itself. So you can see what happens if you do choose an x, what's going to do to the y on the other side. So if you solve this for y, what would you do?
You subtract the 3y over.
You would not subtract the 3y over.
Subtract the x squared.
If I'm solving for y, I want to focus on
Subtract
him
the x squared.
and get rid of the
And then
jump.
divide by having a negative x. That's
So
what I do.
subtract x squared and divide by
3.
3. So you're going to get y equals 8 minus x squared, the whole thing, divided by 3. Or 8/3 minus 1/3 x squared. Now, as I choose values for x over here, you kind of have to use your imagination. If you type in a calculator 8 minus some number squared divided by 3, how many answers are you going to get? Just some number, any number you want to pick on the calculator. If I just type in 8 minus 4 squared divided by 3, how many answers do I get?
Okay, 1.
1. And if I choose any value for x, how many answers am I ever going to get out of this mess? 1. So this thing, by following just order of operations, it's guaranteed to give me one value for y. So therefore, this thing is a function. and I can describe it. For every x, this will generate, getting that mathematical language in there, generations and fun things like that, will generate only one y. And that's the reasoning behind why this is a function. This is where I expect you to be able to explain yourself.
So if the y was squared?
Ah, now that gets a little trickier. So what happens if the y is squared? Let's just change it over to x plus 3y squared is equal to 8. How do you solve this one for y?
You would find what x is.
Subtract the x over,
And then you divide by 3.
divide by 3. So you're going to get y squared is equal to 8 minus x divided by 3.
Then you have to square root the square.
Alright, so you square root both sides and you get y equals,
Square root of 8 minus x over 3.
Square roots aren't,
that's it,
because it could be positive and negative,
Positive
so
and
square
negative.
roots are.
plus
Oh,
or
plus
minus. If you square root both sides of an equation, you have to tag in the plus or minus. Why?
Because you could square -2 and it'd be 4, you could square +2 and it'd be 4.
Okay, let me ask you this question then. What's that equal to?
Plus or minus 1. Or plus or minus, yeah, plus or minus 6.
0.
First thing about square root. Square root of 9 is?
Plus or minus 3.
It's 3. Square root of -3 all squared.
Wait, so
In
what?
other words, square root of -3 all squared equals?
Oh, okay. Then it would just equal 3.
It
It'd be 3.
Because the
And the square root of 3 squared is also 3. So whether it's positive or negative, you want your answer to come out positive. What forces things to do that?
The plus or,
The
yeah,
square.
square root,
What forces everything to be
the
positive?
squares.
No.
makes more sense.
What function makes everybody positive? You learned it in 8th grade.
Can't think of it right now. Oh, the
Absolute
absolute
value.
value.
Absolute value.
Yeah.
By definition, this thing is equal to the absolute value of x. Now, when you have an absolute value equation, you have to separate it into its positive part and its negative part. That's where this is coming from. The plus or the minus, the positive part and the negative part of the absolute value. So, is this a function? Now if I choose x to be, what would be a good number? 5. Yeah, takes me a while. I can't do calculations. So if you let x equal 5, you get 3 in the top, 3 in the bottom, so this becomes 1. The square root of 1 is 1. So you chose one value for x, but what happens to y?
It becomes plus or minus.
You get a positive part and a negative part. So when you choose x to be 5, one of your answers could be
Positive.
+1, or the other one could be
Negative 1.
-1. And because you're coming up with 2 different y values, this thing is definitely not a function.
So basically, if y is squared, then it's not a function.
Correct.
Okay.
Or to the 4th power, or to the 6th power. Any even power, it will definitely not be a function. That's all we can say so far. Not a function because
It is
when x equaled 5, we got 2 y's out of the mess. And that definitely is not what a function is. So how about x squared minus 3y cubed is equal to 8? Change it up a little bit. If you don't know what to do, don't go by shortcuts. If you don't know what to do, the long way is to solve for y and kind of look at it and see what's really going on. So, to solve this one for y, what would you do first? See, I wouldn't. I would take these two and flip their positions.
What allows you to
Yeah,
do
so it
that?
would be minus and positive.
Yeah.
It would be x squared.
But that's just a shortcut. Most people would take the x squared and move it over and get negative 3y cubed equals 8 minus x squared. Then
It would be divided
divide by negative 3. When you divide by negative 3, you can take these two and flip them. So you get y cubed is equal to x squared minus 8 all divided by positive 3. And then cube root. So if you cube root both sides, you get this. Did I go too fast?
Yeah.
Too much.
Okay.
How'd you rid of the negative?
How do I get rid of the negative? If you do 5 minus 2, what's that equal?
3.
3. If I do 2 minus 5, what's that equal to?
-3.
If you flip over subtraction, you're changed the sign. So what happened here is I divided by -3, and to make it +3, I just took the topping and flipped it. It's a neat little trick to know.
You can do that.
Yeah, you could do that.
Wait.
Because they like to teach us the long way.
I know, but I don't do that.
Oh,
They want to make
okay,
themselves
I see
think
what
it's
you're
fun.
Yeah, if you subtract,
So it'll just be x squared minus aka.
if you flip this around, it becomes negative x squared minus 8. The whole thing becomes opposite of what it was. Now, do I need the plus or minus?
No.
Are you sure?
Yes, because it's cubed, so
It's odd, and
It's
odd
gonna
doesn't
be
care if
odd.
it's positive or negative. So, if I plug in x equals 0 in here, I don't care, it doesn't matter. How many answers for y am I going to get?
1.
Just one. Because your calculator would take care of the cube root of -8/3. It would be perfectly fine, and it'll give you a fine answer out of it. So this one is a function. And blah, blah, blah. Same reasoning as this one over here. For every x, this will generate exactly 1 y. So we can kind of generalize. If y is by itself, and there is no other y, by the way, I'm going to write one up here that's a little crazy. Yes, Tony? Oh, dear.
Okay. How's that function? No problem. Because the x just.
Hang on. So, if y is by itself, and you can solve for y directly, this is a function. If y is squared, 4 power, 6 power, whatever, definitely not going to be a function. If it's an odd power, you can solve for it, and it'll be a function. So even on the y bad, odd on the y good, you could care less what happens to the x. The x can be anything it wants to be.
So it can be x cubed, it doesn't matter.
Doesn't matter. X is irrelevant. The concentration should always be on y. Then I can ask silly things like this.
Oh gosh.
Is this a function? What's your gut feeling?
No.
Yeah.
Definitely not.
Because the highest one is squared.
I'm just curious. If I asked you to solve for y, could you?
Yes.
How?
You would do the FOIL for. No, you wouldn't do FOIL. I
Not
think
FOIL.
that.
Definitely not FOIL.
The 3xy can
Get it equal to
No,
0.
you would get it equal to 0, and then you would do like then you would do the grouping.
God, no. Oh, that would be horrible. Here, I'll give you a hint.
You would square root it. Then you would.
Definitely get it equal to 0.
Okay, and then you would.
But if I'm
do-
trying to solve for y, what does this equation look like in terms of y's only? Don't look at it as 4 terms.
You could
Look at it as 3
put that
terms.
as together, and then you can put both y squared minus 3xy together and separate.
Rubik's.
No. Another neat little formula that works with quadratics.
Oh,
You
yeah.
would take out y of one of them.
Quadratics. I don't remember that from last year. Oh yeah. The opposite of that. What?
Yeah.
Oh!
Minus is
Where a is equal to,
That's not the same.
where a is equal to 1, b is equal to negative 3x.
What about the y?
Oh,
But we're
because
solving
y-
this in terms of y. So the b would be negative 3x. The c would be x squared minus 8. But if you solve this, it has a, and therefore it is not
is
a
this like a problem
function.
like that gonna be on our test?
Heck no. I was just kind of trying to push you a little bit over the edge.
I'll start over the edge on the easy stuff.
This is the easy stuff so far.
He's square minus 4
Oh,
Miss Battle was.
I know.
Our teacher taught us that, so
I
I
know.
remember the formula.
I remember. You're not getting me to sing. Tell you that much.
Oh, but you're a wonderful singer.
I know.
That is, it's so much easier to remember.
Okay. Function notation. Very important. Pretty much the rest of the book, you use function notation to prove things about functions, to write formulas that are functional based, fun stuff like that. A lot of people just jump into this, but I want to give the reasoning why function notation exists. So I'm going to write two equations down. We're going to learn lines later, so I'll have to describe this a little different. Do you know how to find a y-intercept on a graph? If you are on the y-axis, what's the only guarantee that you have?
I forgot.
If you are on the y.
If you're on the y-axis, let's say you put an axis system in here and you put a point on the y-axis.
Oh, the y-intercept is 0.
Give me a reasonable coordinate for that point that I just drew. Just reasonable.
1, 0.
It is definitely not 1, 0.
0,
0, 1.
0, 1 would be a reasonable coordinate for it. Give me a reasonable coordinate for this one down here.
0, -1.
0, negative, well, sure, boring.
Yes.
I would have said 0, -2, but that'll
Okay, I'll
be
make it -11.
too late now. So the only thing consistent about y-intercepts is the x-coordinate is always 0. The x-coordinate is always 0. So when you say y-intercept, you're also saying that x must be equal to 0. Guaranteed without a doubt. Any graph, relation and or function, that is true. Okay, so when I say one question, and I only want one answer, what is the y-intercept of y?
Wait, what is the y-intercept of
Of y? See, I don't have a
0,
language to talk about these separately. So if I only want one answer,
So the
the answer to the top one would be what?
0,
the
-4.
x-intercept?
Oh,
Y-intercept of what?
maybe -4.
Would the y-intercept be -4 here?
On the
I
top
don't
one.
know.
On the top one. On the bottom one.
Wait.
The y-intercept for the bottom one would be
The
5.
bottom would be
Be
5.
0, 5, right? But if I only want one answer, and I say I want the y-intercept of the y equation, well, one thing you don't know is which one. And also, when I say y equation, it's kind of weird kind of language. So mathematicians figured out if they want to talk about two functions at the same time, they have to give them names. So the top one is called Frank. The bottom one is called George. Why not? Frank and George. Now if I say, what's the y-intercept of Frank? Which one do you look at?
The top
The
one.
top one. And if I say, what's the y-intercept of George? Which one do you look at? The
Are you
bottom one.
talking about like f of x and
Getting there. Yeah.
f of x and g of x?
F of x and g of x, yeah. So when you see f of x and g of x, it's literally Frank and George. They are names. They are definitely not variables. My favorite thing of all time is when someone takes a function and divides by a function. Like later on, we're going to be dealing with things that look like this. And my favorite way of solving this equation that I've ever seen is this. Which makes absolutely no sense because sign is just like Frank and George. It's just a name. That's all it is. So Frank gets turned into this. And all this notation says, it is the function f in relation to the variable x. When you put these two together, it becomes y. So when you write function notation, your x-coordinate is buried on the inside, your y-coordinate is literally the whole thing. So when you write f of x, you're saying what the x-coordinate is and at the same time the y-coordinate. So if I write g of x, what's the x-coordinate?
Oh, the x.
What's the x-coordinate of g of x?
Oh,
Zero.
X.
Yeah.
Exactly. So x.
That.
What's the y-coordinate?
Y.
G of x. So when you write function notation, you're actually talking about both of the variables at the exact same time. You just have to decompose it a little bit. So when you say g of x, x is the x-coordinate, g of x is the y-coordinate. If I write f of 2, what is it as a coordinate?
no, that 2.
Wait,
F of 2.
2 f of 2.
Yeah.
Perfectly
Go start.
fine coordinate. If we are talking about a graph, and this is actually more important. If we are talking about a graph, here's f of x. Well, no, I should have called it like g of x or something. This is not the same f of x as that one over there. This is not Frank. This is definitely not Frank. And I say, well, here's an x-coordinate. Let's call it a. So a could be 1, 2, 3, 4, 5. It could actually be negative even though I drew it in the positive side. A could be anything. If you go up to the graph and you plot this point, what is the coordinate of this point? Well, A is the x-coordinate,
Then f of x.
and f of
A.
A. The function evaluated at the coordinate A. So we can talk about points on a function that we have no idea what it looks like. In other words, a generalized idea of what a function is. So function notation is really, really powerful. And we're going to be using it in very strange ways throughout the semester. Okay. Pretty pictures. So if I give you a function, something horrible, let's see. F of x is equal to the square root of 9 minus x squared divided by x plus 4. I don't know, making it up. This is too much. This is every class, trust me. A lot of this stuff you should know already. I'm just kind of glazing it over again.
We had teachers like Miss McCrae.
In other
and
words,
Miss Shadow.
they didn't teach
No,
us
I
well.
like that.
Good.
I did not
Guess what
like
you're
Miss
getting
Shadow.
now.
I just got a good teacher.
Well, I'm not so sure about that.
I got an A in Miss McCrae's class.
If
I like Miss McCrae better than Miss Battle.
No.
The
Uh,
first time I ever made a B in math was our Miss McCrae.
Miss Bethel made me get a B in that.
all right. If I want to evaluate something, let's talk about old style first. If I have old style, you go back to y equals 3x minus 4. If I wanted to evaluate this, you'd have to go off to the side and say, let x equal 2. Right? You'd have to say that off to the side. Let x equal 2, find y. Then you take 2 and you plug it in and you get y equals 3 times 2 minus 4. Y equals 2. Right? The problem with this is your x-coordinate is way up here and your y-coordinate is way down here and they're not even close together. Also, you have to add in this extra language to say, evaluate this thing at 2. With function notation, to say I want to evaluate this at 2, I just write f of 2. And it tells me a few things. This, just by writing that in there, is telling me right off that x definitely is equal to 2. Sometimes you want to be able to pull it apart to look at x just by itself without the function notation. To find f of 2, I highly suggest you do this. You write the function without anything in place of the x. This is essence of what a function is.
Is that an A?
That's a 9. That's a 9. Long stem. This is the essence of what a function is. Whatever goes inside of this parentheses just gets stamped into these two positions. This could be 2, it could be negative 3, it could be x plus h, that's later. It could be a minus 5, it could be g minus 3. It could be a whole nother function plugged in there. Whatever gets put in here just gets put in these two positions. So I highly suggest when you're working with a function, this should be your first thing you write down. Then worry about plugging things into
What
it.
if it was like, since that's Frank, what if when it was like Frank is in parentheses f of g, would you put the f of g equation into it?
Oh my gosh, we're going way
You
too
mean
far.
f of g?
F of g of x, we are not going that far.
Oh,
today.
Oh, we're getting there.
I know. Are we going that far today? Please tell me no.
Oh, God, no.
Okay, good.
No, not yet. But that becomes easy because if you just think of a function like this, then whatever goes in those parentheses just gets dumped in those two positions and you're done. Well, not done simplifying it, but at least done. What time is it? Is it? Oh, I'm all done then. Plug a 2 in here, plug a 2 in here, plug a 2 in here, and you get out of this square root of 5 over 6. I think.
Yeah.
I guess it's 2:30 and this web wants to come on in. It's 2:27. Got 3 minutes.
Class doesn't end until 2:47. I can't see.
Graphing functions. There is one guaranteed way of graphing any function that you're given, even if you've never seen it before, especially since you have calculators that you can just plug in stuff and generate y values. So just a quick little example. If you have f of x is equal to x squared minus 2x minus 3. Nice little quadratic function. And if you don't know how to graph it, or if you don't remember how to graph it, you should always be able to at least get a generalized shape from it from generating points. So if you don't know how to graph something, you always generate tables. So on one side you put x, which is also called domain, and the y over here is also called the range, and you're going to get sick of those two words in about 20 minutes. So the way I suggest you do functions is replace all the x's with parentheses. And since you're going to do multiple substitutions into this, it's better not to see the x at all, but just a visualization of where this number is going to go. Where should I start with x? Where do most people start?
0.
Yeah, how boring. Where should you start?
0.
Nope.
1.
Nope.
-1.
Negative.
Most people forget the
Negative
poor
2.
little left side of the graph paper, which is the negative values. I highly suggest you start at -3. If it's a decent graph, most of the behavior is going to happen somewhere between -5 and +5. If you start with -3 and it becomes too big or too small, you can always back up or go forward depending on where you need to go. On the test, I'm going to tell you where to start and where to end. That way you don't have to be guessing and messing around too much. All right, so you take the -3, you plug it into these two spots. -3 squared is?
9.
9 or -9?
9.
Okay, just making sure. -3 times -2.
6.
-3, this becomes 12. That's a little bit too big for most graph paper. Mine is generally 10 by 10. 10 up and 10 to the right. Excuse me. Plug in -2, what do you get?
You get negative.
Or you get 4.
4.
-4.
Plus 4.
Or +4, I'm sorry, -3.
So that would be?
5.
That's a little bit better. I can work with that. So the next one should be perfectly fine until we get too big again. -1. This is 1. 2. -3, better known as 0. What is special about this point, -1, 0? What's it called?
It's the x-intercept. It's the x-intercept.
X-intercept. So this is an x-intercept. When you're dealing with x-intercepts, the thing that remains constant is y is always equal to
What?
0. That's a guarantee. Plug in 0, what do you get? I'm not even going to write it down.
-3.
-3. Because the first two terms will just go away and you're left with that -3. Plug in 1. You get 1.
1 -2 -3.
Better known as? -4. Plug in 2.
That's
2.
4 -4.
4 minus 4?
-3, which
Minus
is
3.
negative.
I already wrote it.
Negative 11.
-3.
Wait, oh, that's a positive. Oops.
-3.
4 minus 4 is 0.
Alright, yeah.
All right.
Go like this.
3.
We're just starting to go back up.
I know.
Like this.
3.
9.
9.
That's gonna
Minus
be
6.
0.
Minus 3.
Settle.
It's going to be 0. 4 is going to be
5.
5. 5 is going to be
12.
12. Does this work with every function?
No.
Please, God, no. This is only working in this case because it is a parabola. All right, and then you just graph it really quickly. -4 is the smallest. 5. Yeah, this should fit nicely here. 1, 2, 3, 4, 5. 1, 2, 5. 1, 2, 3. And then I'm going to say some weird things before I finish this, and you're not going to like it. So, here we go. -3, 12. I'm not going to even try. It's -3 this way and up there someplace. -2, 5. 2 to the left and 5 up. -1,
0.
0. 0,
Negative
0, 0. 0, -3. 1,
3. Negative 4.
-4 is down here. 2,
Negative 3.
-3. 3,
0.
0, 4.
5.
Back up here. Now, this is all I'm guaranteed. Those points. That's it. So what have you been taught to do before? Put a line through them or a curve through them.
Yeah.
How do you know a curve goes through them?
Because it's like connecting dots.
Great. How do you know a curve goes through them?
Because I learned that.
Because you learned that. Because your teacher told you to do that. Because they said, oh, just connect the dots. This is basically what it looks like.
The line.
Now, I mean, you're in pre-calculus now, so I have to go one step further.
Oh.
Just one little step.
I was in pre-cal last year too. That's
Yeah, I doubt you did this step. If you have any 2 points in the plane, how many different ways can you connect them?
One.
One?
No,
Many, infinite?
1, 2, 3,
Infinite.
4, infinite.
I thought you meant like
Yeah,
in a
infinite.
plane.
It isn't a
Or
plane.
like
These are
or no line.
a straight line. Yeah, most people think straight line. But can I connect it any other way than curving up or curving down?
Yes.
Yes. I could have a curve do this. That's perfectly fine.
That one. That was.
There is even the possibility that the graph on this side doesn't even touch the graph on that side. They're disconnected. It's discontinuous. So how do I know that this curve is nice and smooth?
Plug in.
Because you're told. Now, you don't know until later if you can plug in more values. You can plug in negative 1.5, negative 0.5, 0.5.
You
And
would go in the order that you did them in.
yeah, that's not always true though. I can come up with a graph that looks like this on a graphing calculator. Looks very pretty on a graphing calculator. But if you zoomed up on a portion of it, it's doing this. Yeah, it's a little crazy. So what you have to do is if you did the half points, you'd get a point here, you'd get a point here, you'd get a point here, 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 and about there. And if you did enough of them, you start seeing that this curve is actually connecting. But also, when you take 2 points and connect them with a curve, how many points did I just put on the graph?
A lot.
And what's a lot?
A couple.
When you say a lot in math, it means one thing.
Infinity.
You just put an infinity of points, so you're assuming a lot of stuff here. That each one of these points follows right after the next one, infinitely the number of times. So that's just a basic idea. I wanted to throw that at you to make you think just a little bit more of why you connect the dots. So after you connect the dots, you're saying that this entire curve is f of x, instead of just the individual points. That's graphing. While we're looking at this, if we went back to our sets that I said, what's a function, and they only had individual points, some of them were set up like this. And if you just looked at the set of points here, could you tell me if it's a function or not? And compare it to something that might look like this. And how would I be able to tell which one is a function and which one is not?
The vertical.
Vertical line test. And it follows along with x values. This would have the same x value. It would be like -2. In a function, you cannot have x values that
You can have
repeat over different
basically
y
the line
values.
can't pass through
More than once.
more than once.
More than once. But this follows along with the idea that the domain value cannot repeat itself. Up here, each domain value is
Only individual.
only once. So once you have a vertical line test, you can just tell by looking at a graph if it's a function or not. Is it a function?
Yeah.
This one right here.
Yes.
That's a function. Is this a function?
No.
Definitely not. Is this a function?
No.
No. Is this a function?
Yes.
Yes. A lot of people get confused because they start looking side to side and they say, oh no, it's 3 times. You've got to keep your lines completely straight up and down, vertical. So that's a perfectly fine function too. If I do ask this on a test, and it's very rare that I do because most people understand it, you can't just tell me yes and no. You have to tell me why. You have to say, this is a function by the vertical line test because every x value is only hit once. This is not a function because the vertical line test hits at only one spot. It only has to happen once. It hits the graph twice when x is equal to whatever.
We have to put that every time. Can we just put like
I'm
the
only
same
going to ask you
last
like
one?
once if you
Okay, good.
I'm not going to have like 10 million of them. On a test, I'll just have to ask you it once to see if you really know what the heck you're talking about. So, if we're talking about a graph, you're going to have to get pretty good with your artwork now. And we have a function. Make it simple. Something like this. We call this f of x. And the only thing I know about it is this point way up here is maybe 4, 7. It's much better if I had my piece of graph paper. Oh well. When we talk about domain and range, you've got to be really careful with this picture. The first thing you have to be careful about are these arrows down here. These arrows represent two motions. When you're in a coordinate plane, the only motions you get are left, right, up, down. So when you look at that arrow, which way is it going?
Down.
That's the only direction that most people see, but it is also moving
Down and left.
Down.
left.
Yeah.
So it's moving left vertically or horizontally and down vertically. You have to understand this so you can separate the x coordinate from the y coordinate. Because when we start talking about domain and range, domain is your x and range is your y. So this arrow over here is also going down, but it's going to the right. It's constantly moving. Now there are some graphs that have that arrow that do not move to the right very far. They'll have things that look like this. It'll be called a vertical asymptote. And you might have a graph that does this and has an arrow, but this arrow is a little bit different. It can only go up to this dotted line. It doesn't keep on going. So this type of arrow and that type of arrow are totally different. All right, so when I talk about domain, I talk about if I looked at the point set for this entire graph, how far to the left do I go for my x values?
As far as you can go.
Infinity.
Which is known as
Infinity.
negative infinity, because you're going to the left. How far to the right would I be able to go?
Positive.
Positive infinity. So you look at these two arrows and it kind of gives you an idea that if you see an arrow, it is an infinity, one way or the other. Because it's going to the left, it's negative infinity. Because this one's going to the right, it's positive infinity. So we're going to write that domain. Have you ever done interval notation?
Yes.
Yeah, we did it last.
Good, because we're going to use it. Negative infinity is how far you can go to the left. Positive infinity is how far you go to the right. When you do interval notation, you got to be careful. The small one always has to go on the left-hand side, and the bigger one always has to go on the right-hand side. You cannot flip them around, otherwise it's actually incorrect. So the domain of this thing is all real numbers. You can also say that. All real numbers. That's just wordy. But it means exactly the same thing. What is the range? Well, the range is you take every one of the coordinates in your mind and you think of the y coordinates. So that means you're moving up and down. You start with down first and you work your way up. So how far down does this thing go?
Negative infinity.
Negative infinity. How far up does it go? 7. This graph stops at that point, which I'm going to consider the highest point that this thing has. You could care less about the 4. All you care about is the 7. So this thing stops at 7. The parentheses has to change into bracket because that point exists as a point in this function.
So if you put a parentheses around 7, it'd be wrong on the reference?
Yes, because you're saying 7 doesn't exist in this answer. Everything up to 7, it would be like 6.999999999. It would be a lot of 9s, but it would eventually have to end. Trick question. Ready? Trick question. We'll see what you know. What's 0.9 repeating equal to?
No.
I know, but what's it equal to?
Oh.
It's equal to 1. Exactly. Good job. It's not rounded to 1. It is equal to 1. It's exactly equal to 1.
How?
How? I'll let you think about that one. Play around with 1/9, 2/9, 3/9, 4/9, and you'll find out that 1/9 is 0.11111. And 5/9 is 0.55555. So 9/9 would be 1, but it would be 0.99999 if you follow the pattern. All right, how about this graph? What if we had something ugly like this? Ugly. Oh, let's make it really bad. Let's say this point is -2, 5. This coordinate is 3, -4.
What do the open circles mean again?
Ah, open circles.
The open
It's the
circle
bracket,
means
it's
that the
parentheses.
point isn't included.
This point exists for the graph. This point, 3, -4, does not exist on the graph itself, but the one right next to it does. which is
So,
really
like,
hard to explain.
So like,
Like
4,
3.1.
-3. But like, or like,
The point right next to 3, -4 is really hard to define without the
Like
function itself,
3.00.
but it's so close that you can't tell the difference.
like 3, -4.
But 3, -4 physically, that one little lousy little point is not part of this graph. It's hard to explain without limits. You can't talk about limits yet. Yet. So, here it is what we're going to do. This is the function g of x. By the way, what's that one over there then? This one here. Nope, this is still part of g of x. This is called a piecewise function, where the function is broken up into smaller pieces, and there are different portions to it. So don't think of this as f of x and g of x. This whole picture is of g of x itself. So if I say, what's g of -2? Just curious. What's g of -2 equal to? It better be equal to 5. Because the coordinate is -2, 5. Remember, x is equal to -2 and y is equal to 5. All right, if I have g of x is equal to -4, what's x equal to? +3. Because what's -4 represent?
Well,
It
it
represents a
But
y.
that point doesn't exist.
Yeah, but that point
Darn
doesn't
it.
exist.
Yeah, I was gonna say.
That's right.
Quiet. So it doesn't exist, and there is no solution, so empty set. Okay. We'll get to more of those later. Domain. Now, remembering that both of these pieces are the function g, we have to work far left to far right. So as we go to the far left, remember this arrow is moving to the right and up. This arrow is moving up and to the right. If you get those ideas straight in your head, you're better with the infinities. So as we move in from the left, where does the domain start? Negative infinity. Where does it stop? Positive infinity? So all of these points in here are included?
Oh, no, they're not.
Ah, there's a
Because
gap.
it stops and
It
starts.
stops at -2,
Stops here at -2,
and then it doesn't include 3,
but it starts there.
but it starts there,
Yeah,
and then it goes on to infinity.
and it goes on to infinity. So, negative infinity all the way to -2. When I write -2, what symbol do I have to put here? Bracket, it's included. Then I'm going to start at 3, but not exactly at 3, just a little bit to the right of 3. And I'm going to work my way off to positive infinity. Now, there's got to be a symbol that connects these. Isn't there?
Like,
The U, the union.
yeah.
Union, put them all together. The U. All right, range. Now, I have found people do not like two things pointing up in the same direction because they only look at one of the graphs and it gets very confusing. So make sure you're only concentrating on the y-axis. When does the range start?
At negative. It doesn't
Not
start at
at
-4, but it
Well,
does start.
You say it starts at -4 just
It's
to the
parentheses. Yeah.
upside of it.
Parentheses next
So
to it.
parentheses, -4. When does it stop?
Infinity.
It stops
It
at.
doesn't stop.
It doesn't stop. Even though this one starts here, you could care less. This one is going up and it goes off to infinity just as well as
That one.
this one. So it's -4 to infinity.
So if there's -4 was a real point, would you use?
Brackets.
Okay.
Brackets. If it's there, you're going to put brackets. If it's not there, it's parentheses.
So you can't say like 5 instead, or -5 instead of -4.
Where are you talking?
For like the beginning of the range.
Here?
Yeah.
Why would I say -5?
I mean -3. Sorry.
Oh, -3. Which would, but then you're skipping all the values between -4 and -3.
Yeah.
When you put this parentheses, it's saying the next value up from -4. The next real number, but there's so many so close to it. You're just saying, I don't want -4. Pretty good, right? Easy? Good.
Wait.
Tons of homework on that.
Why is it -4? Can you explain?
Here?
Yeah. Why
When you're
negative?
coming from down here, the graph starts at this point.
Yeah.
And that point has a y coordinate of. Because we're moving up the y-axis, so I could care less about the 3. All I care about is that y value. So it has -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, all the way to infinity. As long as there's a graph someplace in the vicinity.
Is there? But there's not. There's no graph on like -2.
There's no graph on the x-axis from here to here.
Oh.
But if you take your look this way,
Yeah.
and they run, I guess if you want horizontal lines at it, as long as the horizontal line touches the graph someplace, it's got a y value. Vertical lines will tell you which one has a x value. Yeah, it's just if you can read a picture, it's mostly what it is. And generally, when I ask domain and range, you'd rather have a picture than me asking right from a function, because that actually becomes a little bit harder. I have to tell you a few things about this. This maximum point here, let's make it -3, -1. This empty space one, -1, -1, -3. Let's make this coordinate 2, 5. This point here, 5, 2. Let's keep it symmetric. Okay. What's f of -3? If we make this function f of x, what's f of -3? -1. If f of x is equal to 2,
5.
x is equal to 5. All right, just curious. So, domain, start from the left, work your way to the right. Negative infinity, because of this arrow right here, it's pointing in that direction. We're talking about domain, left. So it's coming from negative infinity, and it works its way all the way up to, there's a gap.
-3. -1.
Which one, -3 or -1?
-1.
-1. You have a graph, you have a graph, you have a graph,
But
you
it
have a graph.
doesn't include -1, that's just where it stops.
So it goes negative infinity, -1, don't include it.
And then you do union.
Union thing starts up again,
2.
2, bracket,
And then infinity.
and then infinity because this arrow is pointing in that direction, to the right. Yay! That's not a big deal. Range. Negative infinity because this arrow is pointing down, so negative infinity.
Up to -1.
Close, no cigar. Oh, no, you're right. Up to -1. I was looking at something different. Now, which -1 are you talking about?
I'm talking about the one that's included.
Yeah, but there's this -1, and there's
No,
this
I'm talking
-1.
about that
Oh,
one.
the Y value.
The y value one.
Yeah.
Okay. Bracket.
What do you
Union.
What do you
And then a
call the
bracket.
apex up there? What do you
Ah,
call
we'll
it?
get to that in a second.
Okay.
It's got a special name.
Yeah.
It starts again at
Bracket.
bracket 2,
And then infinity.
and then to infinity. They look exactly the same answer, but they're totally different. This one is talking all about x values. This one is talking all about y values. Now, these points have special names. Anybody know what they are? Ah, the relative word. This one here is called a relative max, or maximum if you want to go out for the whole word. Now, it's called a relative, and it's not called just a regular old max, because it says this point is the biggest guy in its own neighborhood. That little circle that I've drawn is called a neighborhood. He is the biggest or the richest person in this neighborhood. Therefore, he's called a relative max. But is he the richest person in the world?
No.
No. So he's called relative because in his neighborhood he's the richest person, but there's other people that are more rich than him. That's this other part. This point is called a relative min. He is the poorest person in his neighborhood, but obviously these people are poor. So he's the lowest income earner in his neighborhood, but there are poorer people in the world. Imagine being the poorest person in Manhattan. I would take that any day of the week.
It would be the worst person in New Guinea.
New Guinea. Poorest person in the richest neighborhood. Now, if you have a graph like a parabola, it looks like this. If it's facing upwards, this point is called a absolute min. And if you have a parabola going in the other direction, this point would be called an absolute max. It is the absolute richest person in the world or the absolute poorest person in the world. Yeah, in its neighborhood. No, it's not a neighborhood anymore.
So is it relative because it's not?
It's not.
Like segregated?
It says it's the maximum, but it's not the biggest point ever
Yeah,
because there's more.
is it relative because that one isn't like a full U?
No, I could care less about it being a full U. All you do is look in the neighborhood. Give you a different picture.
Like,
What's the difference between absolute and relative?
If you
Absolutely, there's only one.
no, I mean,
The ones
Is that
that
what you're talking
absolutely
about?
have 2 arrows on them. Ones with relative only 1.
if you have a graph that looks like this, which is possible, kind of crazy. This point over here, what would you call it?
It's an absolute.
Nope.
It's a relative.
It's a relative because over here the graph is going down to negative infinity. So this is a relative min. This one here is a relative max, even though there's a bigger point over here and it goes off to infinity.
Would that be a relative max too?
This would be a relative max. This one is a relative max. This one is a relative min. This one here,
Relative min.
relative min. And this one is a very flat min.
And then there's one more.
Oh,
and then
and this
there's
would be a relative
max right there.
max. There is a whole study of mathematics of finding all of those points.
What is like since the one that you circled last before the other one?
This one?
No, other one.
This one?
Yes, that one. Can that be like a relative max compared to the lowest one over there?
No, you don't look at the points individually. You look in their neighborhood. Because that thing is curving down and you're at the bottom of it, it's a relative min.
Alright, say on the graph over here to the left, if you didn't have that part,
That's an
Yeah.
absolute max.
Yeah.
If you got rid of that one, this one is a absolute min. Guaranteed.
It's relative because there's 2 parts.
No, it's relative because
There's
he's the richest one in his neighborhood, but these people over here are richer because they're higher. And it's still part of the function g of x. Even if I connected these points, added in this part of a curve maybe,
It'd still be the relative.
this would still be a relative max and this would still be a relative min. It doesn't matter that it's disconnected.
Wait, but
Because it's one of the high.
I know
It is a high point, but it's not the highest point.
But say it was like switched around and the bottom part, that the left side of the graph would be on the top.
You mean rotate it?
The left side would be on the top and then the right would be on the bottom. Would that be absolute or would that still be relative?
Both of them would still be relative. This way, if you flipped it over, it would be a relative min, and if you flip this one over, it would be a relative max. Because they're still part of the same function, even though they're broken apart.
Okay.
I know, that's weird. You get used to it. Because you're so used to graphs connecting to one another. And the next topic is, piecewise graphs. Piecewise functions. There is a realistic application of these type functions. For instance, if you work for commission, anybody work for commission? It's the worst way to work unless you can really sell a lot of things. If you work for commission, you get 2 parts to your pay. Part A, maybe you make $200 a week. Part B, if you sell more than, well actually let's keep it simple. If you sell, let's keep it hard. More than $500, you get 5% on anything you sell above $500. So if you sell $600, you get 5% on $100, which means you earn $5. So then your pay becomes $205. So this thing depends on if you actually make it over that $500 threshold. So if you don't make more than $500, you have a condition. Let's say X is the amount of money you sold. Maybe you work in an electronics department and you want to sell big screen TVs, and they should bring you in a commission because most of them are more than $500 unless they get a cheapie. All right, so you get 2 possibilities. Number 1, X is less than $500. Well, less than or equal to. If you sell less than $500 worth of material, how much is your pay? $200. How exciting. I know, isn't it? If you sell more than $500, it gets a little trickier. If you sell more than $500, you only earn 5% on the amount of money that you sell over $500. So when I say I sell $600, I only earn commission on
100.
100 of the dollars. So I took my 600 that I actually did sell and I subtracted away that 500. So this is the variable X, because this 600 could be $700 sold, $800 sold. So part of my equation over here is going to be X minus 500. I want to take that. This is my amount of commission. Multiply that by
2, no,
One multiplied by 5%.
5%, so it's 0.05. This would be how much I'm earning in commission, but I also earn,
$200.
so you'd add 200 bucks. So this idea of a piecewise function is very applicable to the real world, especially in this case. Phone calls are also piecewise functions. You know, you make a phone call, you get charged right away for 1 minute, even though you only talk, long distance I'm talking about. Even if you only talk for 10 seconds, you get charged for a whole minute. So that's one function. Then you get a new function if you talk to for 2 minutes. You get another function, and they're all broken apart, and it looks like a staircase going up as a graph. So this is what's considered a piecewise function, and it has conditions to it. If you make less than $500, you earn 200 bucks. If you earn $500 or more, you can plug it into this formula and find out how much you actually make for the week. So, how do we work with piecewise functions that are just randomly given to you? Like on a test day. If I give you f of x is equal to, and this is generally how they're written. They put a little bracy in there, and it tells you that you're going to have parts to this function. And I say that this one is x squared minus 9 when x is greater than 3. Let's make it square root of. And the bottom one is the square root of 9 minus x squared when x is less than 3. I gotta be really careful here. That one's perfectly fine. This one I have to be a little bit more cautious. Well, actually, no, that should work. No, less than 3.
Okay.
No, it won't work.
What was that? Wait. You're really confusing me.
There.
Go back and forth here.
I just want to make sure it doesn't kill anything.
What do you mean?
What do I mean? If I let this thing get too big, this becomes 9 minus 10, and 9
And it
minus
would
10,
be -1.
and square root of
make it
negative 1 is
like,
it's not undefined.
It's
I. It's I.
yeah.
So I wanted to avoid that, so I'm going to squeeze it between -3 and +3 just to be safe. So if I say find f of 2, the first thing you have to do is kind of quantify which of these two pieces am I really looking at. So here x is equal to 2, and you say, well, is x 2 bigger than 3? No, so it can't go into the first part. It has to go into the second part, I hope. Is 2 between -3 and +3?
Yes.
Yeah, so then you would turn around and just plug it into this function, which gives you, what, square root of 5?
Yeah.
So f of 2 would equal square root of 5. If I tried to find f of 5, it's definitely not the second one because it's not between -3 and 3. You would have to go into the top one, so it becomes the square root of 25 minus 9, better known as the square root of 16, better known as 4, which is a nice number. But the real world doesn't work on nice numbers. So that's how you operate with a piecewise function. You don't plug it into both pieces. You plug it into only one piece because you can only have one y value associated with it. And it's told by the conditions at the very end. Some books will put a dotted line here, or a solid line to separate your conditions away from your functions. Don't let that fool you. As long as you have two pieces, you have to have two conditions. And these domains cannot overlap. They have to be totally separate. Notice this one is greater than 3 and this one has the equals down here. Usually one has the equals, one doesn't. If they both don't have it, that's fine also.
So, like, what happens if it does go over the equals? If you just put
If they both have equals, let's say they both had equals,
Yeah.
then it's not a function.
Yeah.
Unless, and this is a big
boy.
unless, Unless, if I plugged in 3 into this one and 3 into this one, they came up to the exact same y value. Where one started and the other one landed right on top of it, that's perfectly fine. But if they were separate, then it's not a function. But that's not usually the case. Nope. Graphing one. Real quick. If I have a piecewise function that is g of x is equal to, I'll keep it simple, 2x minus 3 and 4 minus x. This one, we'll let it be for less than 2. And this one will make it greater than 2. Alright. So if I'm going to graph this, the only way I've shown you how to graph a function so far is table. And this one is going to require a nice little table. Actually, 2 of them. Why 2?
Because you have 2 functions.
2 pieces.
Or
2 pieces.
not
So I'm going to do 2 tables. This table, when I plug in x's, is going to start where?
It's going to start at, yeah, 3,
2.1.
at 1.
Something.
How about at 2?
But it can't,
Uh,
because it's,
I know, but how about at 2? What can I do on the graph to say it doesn't exist? Open
Empty
circle.
circle.
So I can plug in 2. And I'm going to plug it into both of them. And the first one is 2 times something minus 3. The second one is 4 minus something. Start both of them at 2. I'm going to do one at a time, but I wanted to show that you really want to start them at the boundaries that this thing's set up. So if you plug in 2, you get 2 times 2 is 4. 4 minus 3 is 1. What would be your next value you plug in over here?
1.
Why 1, not 3?
Because you have to go, it's
Yeah.
less than.
I have to go less than 2. I cannot go greater than 2 for this function. So 1, which would be 2 minus 3, which is negative 1. 2, 0, negative 3. And that should be enough. This is a line. I'm not going to get too much detail about it. This one over here, if I plug in 2, you get 2. If I plug in, what would be my next number here? 3, I would get 1. 4,
You get 0.
you get 0. That should be enough for those. So when I set up my graph, 1, 2, 3, 4, 5. I highly suggest the first thing you put in this graph is a vertical dotted line at 2. Because on this side of the dotted line, something happens different than on this side. Because a lot of people get pencil happy, and when you draw a line, you draw it straight through. But if I start a line over here, it has to stop at this boundary. And if I draw a line over here, it has to stop at this boundary. So nothing crosses over this dotted line. So plot our points, 2, 1, 2, 1. What do I put here, though? Open circle for sure. Next one is 1, negative 1. So 1, negative 1's down here. And 0, negative 3 is down here. So this is a line. We'll be learning about those later. Going down in that direction. But it does not pass through this dotted line and continue on up here in the first quadrant. All right, the second part of the graph starts at 2, 2. So I go to 2, 2, put a open circle for sure. And then plot 3, 1. 3, 1 is here. And 4, 0 is here. And we get a line going this way. So this piecewise function comes up, stops here, jumps up here, and continues on its merry way. It almost looks like an absolute value equation. And absolute values are a piecewise function. Because if you truly define the absolute value function, it is equal to positive x when x is, how do you read this in English?
Greater than
It's greater than or equal to 0, but how do you read it in English? X is
Bigger.
begins with a P.
X is positive.
Positive. When you see something like this, do not read x is greater than or equal to 0 because that tells you absolutely nothing. Read it as x is positive. Therefore, the absolute value of a positive number is itself. How do you read this in English?
X is negative.
Definitely x is negative. What happens when you take the absolute value of a negative number?
It becomes
Now just go
positive.
How do you make it positive?
By
Multiply it.
the absolute
Multiplying it by?
Itself.
Close
Or
enough.
negative
Negative
one.
1. So this becomes negative x. So you get this piecewise function where the absolute value of x splits into two pieces. This is a positive slope value, so it would go this way. This one is a negative slope value, but it comes down from this side. So negative slope, positive slope, you get an absolute value function. But it is a piecewise defined function, which is kind of